Risk management, evaluating risk and applying PERT technique. First up, we'll see evaluating risk to the schedule. If a task in a project takes longer than planned, we might hope that some other task might take less and thus compensate for this delay. So let's consider task A and say task B in a project. Task A takes 10 days to complete, and for some reason we couldn't finish it within 10 days. And now we could only hope that we will finish the task B faster so that we will stay on schedule. PERT is a technique which takes into account the uncertainties and the durations of activities within a project. A drawback of PERT is that there can be a tendency for developers to work to the schedule even if the task could be completed more quickly. So let's say task A, which takes 10 days, could be completed within 5 days. They will still delay the work or finish it in 5 days and take the next 5 days off. This will exploit the chance of finishing the project faster. The project manager can also be a little careless and not make the team start the next task. Applying per technique. Before we see applying per techniques, we'll do a quick revision on what is activity on arrow networks. Activities are represented on the links and the nodes represent the events of activities. The network will have only one start node and one end node. The link will include the duration of the activities. The time will move from left to right. The nodes are numbered sequentially and the network will have no dangles and loops. Using PERT to evaluate the effects of uncertainty. PERT was developed to take account of the uncertainty surrounding the estimates of task durations. It was developed to handle large software projects which are very expensive and prone to more risks. The PERT uses three time estimates: most likely time, optimistic time, and pessimistic time. Most likely time, denoted by M, is the expected time taken by the task under normal circumstances, considering all the risk, normal working time, and so on. Optimistic time, denoted by A, is the shortest expected time in which the task will be completed. Here we expect somehow, say some miracle happen and all the developers start working 24/7 without any breaks, then by when will the project will be completed? The name itself says optimistic. Next, we have pessimistic time, denoted by B, which is the worst possible time by which the task will be completed. Here, we say all the risk we assessed happens and some additional risks come in and it's chaotic. Then by what time will the task will be completed? However, we exclude the acts of God and warfare. So we have activities A to H, and A, B, and F have no precedences. That means they can be started right away, whereas C can only be started after activity A is complete. D and E can only be started after activity B is complete. G can only be started after E and F is complete. H can only be started after C and D is complete. We also have given the optimistic time, most likely time, and the pessimistic time for each of the activities. All these are in units of weeks. We use these three time estimates and come up with something called as expected duration TE. We find it using the formula TE is equal to A plus 4M plus B divided by 6. That is the optimistic time plus 4 into most likely time plus pessimistic time. So now we calculate the expected duration for each of the activities. So considering activity A, we have 5 plus 4 into most likely time M6 plus 8 divided by 6, giving us 6.17. Considering B, we have 3 plus 4 into 4 plus 5 divided by 6, giving 4. And similarly, we do for all the activities. The expected durations are used to carry out forward pass. PERT does not indicate the earliest date by which the project will be completed, but the expected date, that is the most likely date. So rather than saying the completion date for the project is, we say we expect to complete the project by. PERT labeling convention is as follows. So earlier we saw we use nodes to represent the events, and it has four divisions, one representing the event number, the expected date, one with standard deviation, and the last one with target date. Now we draw the network. So we have the starting event, which is event number 1. Obviously, the expected date will be 0. Activity A happens, which leads to event number 2. Activity B leads to event number 3. We can see from the table that soon after A and B, we can start C and also D respectively. So D and C happens, which leads to event number 4. This means we can start event number E as well because B is already done. We can also start F because it has no precedence. And E and F leads to event number 5. G can be started after E and F, which is already done. H can be started after C and D, which is also already done. So H and G contribute to the final node, that is event number 6. Now we fill in the expected date for each of the events. Using the formula, we have calculated the expected durations for each of the activities. Now we will do it for the events. So if there is only one activity happening before and there is only one path to follow, the event will have the same expected date as the activity. So event number 2 will have the expected date of 6.17. Event number 3 will have the expected date of activity B, which is 4. Event number 4, we have to consider the two paths. There is A to C and B to D. We on all along we also fill up the activity, I mean expected durations for each of the activities. When we have two paths, we add up the expected durations for each path separately and take the maximum. So we have A to C giving 6.17 plus 2.83, which is 9. B to D giving 4 plus 4.08, which is 8.08. So comparing both of these, A to C have the highest. So we fill in 9 as the expected date for event number 4. Similar pattern is followed for event number 5 and event number 6. And we use up all the expected durations and conclude that the entire project is expected to complete within 13.5 weeks. Activity standard deviations. This is used to measure the degree of uncertainty or risk. As we know, uncertainty and risk are two different things. Risk is when we know all the outcomes and the likelihood of those outcomes. Uncertainty refers to the situation where either the outcomes or the occurrences are unknown to the decision maker. Here we are finding the standard deviation for each activity. This will help us to estimate the degree of uncertainty or risk for each activity. The formula is S is equal to B minus A by 6, that is pessimistic minus optimistic divided by 6. It is the standard deviation is proportional to between the pessimistic time and optimistic time. Note this standard deviation is for the activities, not the events. Then we find the standard deviation for each of the activities. So we have 8 minus 5 divided by 6 giving 0.5. 5 minus 3 divided by 6 giving 0.33. 3 minus 2 divided by 6 giving 0.17 for activities A, B, and C respectively. And we calculate the standard deviations for all the activities. After calculating the standard deviations for all the activities, we fill in the standard deviation for the events. So event number 1 will obviously again have 0. Event number 2 will have 0.5, which is the standard deviation for activity A. Event number 3 will have the same standard deviation of activity B, which is 0.33. Event number 4 will have 0.53. Let's see how. So here again we have two paths, A to C and B to D. If there are two paths, then the square root of their sum of squares is taken. So considering the path A to C, we have the square root of 0.17 whole square plus 0.5 whole square, which is giving 0.53. Then we have the next path, which is B to D. that will be square root of 0.33 whole square plus 0.25 whole square, which are the standard deviations of B and D respectively, and that gives us 0.41. The highest among this is 0.53, and therefore event number 4 will have 0.53. Similar steps is done for event number 5 and event number 6. Next up, we have likelihood of meeting targets. So here we are assuming or considering that the entire project will be completed within 15 weeks. That means the target date of event number 6, which is the final event, will be 15. And we say that event number 4 and event number 5 will be completed by 10 weeks. So what we are doing is we are basically setting a target date for event number 4 and event number 5. PERT technique uses the following three-step method for calculating the probability of meeting or missing the target date. So first up, we calculate the standard deviation for every event, which is what we did 2-3 slides before. Then we calculate something called as Z values. These can be calculated only if the target date is set. So that means we are calculating it only for event number 4, 5, and 6. After finding the Z value, we convert it to probability. The Z value is calculated with each node that has a target date. It is the number of standard deviations between the expected date and the target date of the nodes. The formula goes like Z is equal to capital T minus TE divided by S. The target date is capital T, which we are considering or assuming. And then we have TE and S, which is the expected date and standard deviation, which we calculated using the 3 time estimates we considered. Now we are calculating Z values for event number 4, event number 6, and event number 5. The Z value of event number 4 will be 10, which is the target date, minus 9, which is the expected duration, divided by the standard deviation 0.53, which will give us 1.8867. The Z value for event number 5 is 10 minus 10.5 divided by 1.17, which is equal to minus 0.4227. And calculating a Z value for event number 6 would be 15 minus 13.5 divided by 1.22, which is 1.23. So to sum up, we have event number 4 with Z value 1.88, 5 with minus 0.427, 6 with 1.23. Now we plot this in the graph. So we have a graph which has Z value in the x-axis and probability of not meeting the target date in the y-axis. So I have represented each of the event in different colors. So 4 is red, 5 is green, and 6 is blue. The graph is the equivalent of tables of Z values, which is also known as standard normal deviates. So 4 has the Z value of 1.88, which falls somewhere here, and it cuts the graph at this point, which is nothing but, which comes over somewhere over here, which is 5%. So the probability of not meeting the target date is 5%. Event number 5 have the Z value of minus 0.427, which will fall somewhere over here, and that cuts the graph over this place, which is somewhere around 65%. Event number 6, which is represented using blue, is 1.23, which will fall somewhere over here, and that cuts the curve at this point, which is somewhere around 11. So the probability of not meeting the target date for event 6 would be 11%. To sum up, this implies that there is 5% risk of not meeting the target date of event 4, 65% risk of not meeting the target date of event 5, 11% risk of not meeting the target date of event number 6. Next up, we have advantages of PERT. It is mainly focused attention on uncertainty. It is used to calculate standard deviation, which helps us to rank the task based on their degree of risk. Example, we have activity F that has a standard deviation of 1.17 and C that has a standard deviation of 0.17, which is comparatively less. If we set a target date, we can find the probability of meeting the set target date using expected time and standard deviation. By setting target dates along the critical path, we can focus on those activities posing the greatest risk to the project schedule. So to wrap it up, there is a comic. A guy says we have planned the whole project until 2013 and we have detected and minimized all the risk. Now there's only one tiny little thing that could come in our way. They both stare at each other and the other guy will be like, oh, the reality. So the green guy says, yep. So no matter how much we plan the work and analyze the risk and take all kinds of precautions, the only way to know whether it will be successful is if we work the plan. So plan the work and then work the plan. So I hope all your plans work out, and those who don't have a plan, let the plan of not having a plan work out. Thank you.